Hello everyone, and welcome back to a new video in programming the Finite Element Method using MATLAB. In this video, we're going to do a little housekeeping here. We missed something that we should have done, which is in the entire calculation of equivalent nodes, we missed the check of is inside segment or not. And this check is to be done for the distributed load and for the bar forces, or the loads that are on the bar. Now those checks I haven't done yet. For now, I assume it's true. But that's not the case because the load could be outside the fem bar. In that case, nothing happens. So how do we detect if a load is inside the fem bar? That's what we're going to do this time. So before I start, I want once again to give the reminders that this is part of two video series. One about the fem bar theory plus programming, and one about the programming only. And as per usual, my dear channel members would have access to the entire source code, each lecture at a time. But if you are not a channel member, then don't worry, because in the end, every single line of code is written in front of you. You can write along and you would have the exact same code as mine. So with that being said, and without further ado, sit back, relax, and enjoy the show. Okay, so now we need to program two functions here. One of them I'm going to call is BarForce, let's call it, inside segment or fem bar. Let's call it segment for now, okay? And to do this check, we need to pass in the bar force, we need to pass in the STR line, we need to pass in the fem bar, okay? So this is something we need to do. Of course, there will be an error because this hasn't been implemented. Similarly, I'll copy this entire thing and basically go to the distributed load. So I will collapse this. In the distributed load here, I'm gonna paste that. And here I will call it is distributed load inside segment. Okay, so I have two functions that I need to check. For the other one, I think it's better to call this load, because I want to be consistent, so that's the load. And now we need to check that. At the very bottom of my code here, I'll declare two functions. One of them checks if the bar force is inside the segment. One of them checks if the distributed load is inside the segment, or touching it at least. So let's start with the bar force because it's easier. Of course, here the answer is inside segment, and this is going to equal the call of the function is bar inside segment. Here, of course, I need to pass in the object, and I will end this. Again, I need to copy this entire thing and paste it, and here is distributed load inside segment, and here I'm passing in the load. So I need two functions. Let's deal with the easy one, bar force. Now, if you survive the equivalent nodal forces, then this should be a joke for you. So let's go to the bar force here. Let's declare some stuff. First of all, str node 1, that's the starting node of the str line. I will tell you later why we need them. Fem node 1, that's the starting point of the fem bar, dot fem node 1. By the way, I should put here dot node 1, I forgot. And fem node 2, this is fem bar dot fem node 2. I have them. Now I'm going to declare distance segment start. I have done this before somewhere. I really forgot where. I think I've done this somewhere here. Yeah, that's the one. Let me copy those two things. And please check out the previous videos for explanation what this means. I just control paste this here. So I have distance segment start and distance segment end. The distance segment start, I will explain what those mean in a moment. Now here, I also need the distance load, or the distance of the load. So here I'll call this distance load, and I will go and ask the str line dot length to be multiplied by the load dot relative location. Okay, and now here is the condition that returns true. So if the following condition happens, then is inside segment is going to be true and we can return. Otherwise, is inside segment is not going to be, and we return false, return to the caller and end here. Okay, so what is this mystery condition that we need? Let me explain this to you. The load must be between the start and the end, and to do that there are multiple options. Option 1, the load starts at the segment start. Option 2, the load ends at the segment end. And option 3, the load is between the segment start and the segment end. If the load is at the segment start, how do I measure this? I have the segment start, which is the position of the start of the segment, the fem bar, from the start of the str line. I also have the segment end, which is the distance of the fem bar end from the start of the bar, and I have the distance load. If it's at the start, then basically the distance segment start and the load will have the same value. If it's at the end, then distance load segment end will have the same value. And if it's in between, the distance load will be more than start and less than end. There is no equality here because there are mathematical errors. So I need to do the usual shenanigans with epsilon. So here, let me just check if epsilon is constant or not. Epsilon is not a constant, so I have to call the object here. So here I will ask the question, absolute distance load minus distance segment start is less than or equals object.epsilon. So basically they are very close to each other. If that's the case, then it's inside the segment. Or another condition is absolute distance load minus distance segment end is less than or equal object.epsilon. In this case, we are at the end. Or distance load, now this needs brackets here, because I'm going to call distance load is more than distance segment start, and at the same time, distance load is less than the distance segment end. I hope this makes sense. Those are the conditions that cause us to be inside the segment. This is for the BarForce. Oh, I should call it load, by the way, here. And yep, that's the check for a bar concentrated load. But that's not everything, because we need to check for a distributed load. For the distributed load, some shenanigans are going to be the same. Some shenanigans are not going to be the same. I'll copy this entire thing and paste it and change whatever is needed. So I paste this here, and let's see. Let's define some helper values. str node 1 equals str line str node 1. That's true. This is true. That's true. All those are needed. Distributed load now has a start and an end. So I need to call in for a start, which means relative location 1. I forgot. Is it 1 or start? Let me go to line distributed and see if I called it start or 1. I called it start. Okay, so it's relative location at start. And then I have distance load end. And that's str line dot length multiplied by the load dot relative location end. Fantastic. Okay. Now we get to our condition. What are our 4 conditions? Any one of them is enough to say that the load is affecting the fem bar. Distance load start, same as distance segment start. This is condition number 1. Distance load end, same as distance segment end. That's condition 2. Condition 3 is it starts inside the segment, which means here that the distance load start is more than the distance segment start, and at the same time, the distance load start is less than the distance segment end. This means it starts inside the segment. Or, let's go to condition 4. The distance load end is more than the distance segment start, and at the same time, the distance load end is less than the distance segment end. This is the 3rd condition, and that means that the end is inside the segment. And the last one is that the distance load end is more than the distance segment end, so it overshoots the segment. But at the same time, the distance load start is less than the distance segment start, so it starts before the segment, so it engulfs the entire segment. This is the condition that causes true. So those were the to-dos I had to do in the equivalent nodal force calculation. We have done this now, and with that being said, I think I can say that the programming session for the equivalent nodal forces has been accomplished. There is still a ton of debugging to be done, but I will keep this for later. For now, I just want to make a full circle where I get the nodal displacements to kind of get something that might make me happy. It's been a long time since I touched my viewer, and I want to touch it when I get nodal displacements. But that's of course something for another video in the future. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a finalization-sized shout-out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is a Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.